Okay, welcome and thank you for coming to this session called Frontiers in Magnetic Microscopy. So we hope to cover some the new developments in magnetic field microscopy at the grain scale, the micro scale, but also the way we conveners thought about it. It's really more also about magnetic imaging and at the grand scale, at the much larger scales. So hopefully you'll see a bit of both of that. But at any scale, one of the persistent problems in magnetic microscopy and imaging has always been, how do you analyze the data? You got lots of beautiful pictures with lots of colors on it, but how do you reduce it down to a usable set of parameters? And that's what the first talk's going to be about.
Thank you. Thank you for the invitation. And I would like to say that it's great to see that we finally have like a magnetic microscopy session, that there is enough critical mass of people now with instruments and applications that bringing new ideas and new techniques. So it's really nice to see this area growing. So I'm going to talk today about how can we estimate that moment from magnetic microscopy data. And the goal is, how can we use magnetic microscopy to conduct paleomagnetic studies? Anything? Oh, there you go. First, I would like to acknowledge people that contributed in various capacities to the results that I'm showing here, including Josh, Nono, and Clenio. So when we talk about magnetic microscopy, you're always talking about an inverse problem. And why is that? The most basic fact is that we cannot directly measure magnetization except at a very thin layer, surface layer. So because of that, what magnetic sensors do is that they measure the field, magnetic field produced by a source distribution, by your geological sample. But we're not interested in that field. We're interested in the sources that gave rise to that field. And there is your inverse problem. So fundamentally, what can we say about the sources from this field that we measure, right? So let's start with like a simple inverse problem. Suppose that you're outside and you want to measure the height of a tree. You can climb this tree, drop a tape measure, ask someone down to read it, or you can solve an inverse problem. So in this case, it's a simple inverse problem. You can look at the shadow, measure the shadow, and if you have an inclinometer, you can measure this angle alpha, and you can determine the height of the tree from this information. So it's very much what we're going to be doing. We're not interested in the magnetic field of the sample per se, which is the shadow. We're interested in the height of your tree, which is your magnetization distribution or any characteristics of interest of your magnetization. But we can only measure the shadow. This inverse problem is simple because the tangent function is what we call a bijection. So for any value on the y-axis here, there's only one value on the x-axis. So we can, if you know the y, you can determine the x value. Not all functions are like that, like a parabola is not a bijection. And what you have is like, if I tell you, oh, I measure 2, now you don't know whether you are talking about minus 1.5 or plus 2.5. Those two x coordinates give you the same measurement, right? The same y value. In terms of magnetic microscopy, so just as a warning, I'm going to show some like ugly equations here, but it's unavoidable because this is essentially a mathematical problem. But I really would like you to try to take a high level approach. We're not interested in the details of the equations, but much more in the structure of the equation is what they can tell us. So in terms of magnetic microscopy, you can assume that you have a source volume of half space, and that you're going to take your measurements above this at a plane. The relationship between magnetic field and magnetization is quite complicated. It's given by this equation, which is called the Fredholm integral equation of the first kind. For people that are more math savvy, they might recognize that that's a convolution. So that's a very well studied type of integral equation. But you can think of this as this kind of black box that we call a linear operator that takes a vector function that is your magnetization and spits out another vector function that is a magnetic field. So when you study electromagnetism, that's all you did. Someone gave you a current on a wire and then you computed the field. So you were doing the direct problem. But here, what we're interested is in doing the inverse problem. So given that we know we have measurements of magnetic field, what can we say about the magnetization? And this is a somewhat complicated problem. So to make this a little less abstract, this is a map, magnetic field map. All the maps I'm going to show here are squid microscopy maps. So this is a squid microscopy maps of Hawaiian basalt here on the right. And on the left, I'm showing, after I solved the inverse problem, what is the magnetization that gave rise to that magnetic field that I measured. And so you can think of this linear operator as this box that is mapping that image into this image. Because to solve for the whole magnetization distribution, it's usually you pose a non-unique problem. It may be beneficial to take a different approach for certain classes of samples. And that's what we're going to talk today. Instead of solving for the whole magnetization, we're going to do something similar to what the 2G magnetometer does. It gives you an estimate of the net moment or the integral of the magnetization of the sample that you have on your instrument. So instead of trying to see how the magnetization is varying in space, you're essentially lumping everything together and you're saying, well, what is my average behavior, right? That's your net moment. The problem is, even though the solution is unique in this case, the inverse problem is still will pose because that operator is discontinuous for the planar case. The simplest way of doing this is if you have sources that are small enough or uniformly magnetized, they may behave quite similarly to a dipole. And so what you can try to do is to fit a dipole model to your data. And we have used that successfully on many applications. And what is important to recognize is that you have coefficients which are in magenta over there. They're multiplied by these functions. And what you're going to do, you're going to try to determine those coefficients based on projections of your data onto those functions. This is pretty much like what you do, what we call inner products. In the case of the dipole is fairly simple, but here's a complication. Because you don't know where that dipole is, that problem is not just projections. It's not just a linear problem. So because you also have to find where the dipole is located, this is a nonlinear inverse problem. And how we go about it, there are different options that you can do this. What we did is that we use an optimization algorithm to minimize the difference between what the field that the model is created and the field that you measured. And you're going to adjust those parameters to minimize that difference. So here's an example of a field map of like a real sample on the left. This thing is extremely weak, as you can see here. The moment that we estimated is 3 × 10⁻⁵ centimeters squared. And you're getting now to the limit, and this is one of the selling points for magnetic microscopy, is that everything is magnetic. Once you get down to this sensitivity limit, your glue is magnetic, your substrate is magnetic, and the ability to see where contamination is and to focus just on the part that matters, it's critical. And the big advantage of microscopy. So in this case, if you adjust the 6 parameters, that's the result that we got. These are the residuals, which are essentially noise plus or contamination plus some kind of structured things over there. So we applied this to zircons, we applied to chondros, we applied to a lot of samples that can be well represented by single dipoles. Here's a map of a zircon. You also can see, I just want to highlight, we're talking about sub-nanotesla fields. So these are very, very weak samples. And that's the map. And this is alternating field demagnetization. And here's what you start to see. As you demagnetize your sample, now all of those background sources start to come to the foreground. And you can actually use them like here. Like these dipoles here to the side here. You can use that almost like a marker to localize where your zircon is, because your zircon is becoming so weak. And of course, you want to exclude this from your measurements, right? From your estimations. And that is the big advantage of microscopy. If you were to pop that sample on the 2G, you would see all of those sources, right? Whereas with magnetic microscopy, you can really see what's your region of interest. And sure. No.
Why don't you want to know about that other dipole?
Because that is not my zircon. Because I know from optical images that that is something.
Look on the other side of the spectral amount. So you're just saying that that's your noise level.
It's not, I'm not going to call it noise because it's not instrument noise, but it is contamination. We like to call it contamination. It's like everything that you're going to use to mount this thing to measure is magnetic. So you can get like Zydeville diagrams from this, and this is actually a rare instance where we had a sample with 10 to the minus 14 or sub 10 to the minus 14 meters square that actually gave a coherent demagnetization. Most cases, there's not enough magnetic material down to those moment levels to constrain anything. You're just going to see a demagnetization moving about. But then we also measured other things, and these are speleothems that Josh got from Kravis Cave in Missouri. And we have an ongoing collaboration where we're trying to understand what are the ultimate temporal limits that we can extract from speleothems. And once we map those things, we're like, whoa, this is completely non-dipolar. What are we going to do about this? How can we process these data? We can try to compute a full inversion for magnetization, but this is clearly not unidirectional. So we're going to have a lot of non-uniqueness issues. So the first attempt is, okay, let's do upward continuation. Let's do some mathematical calculations as if we measure this from a higher distance. And by doing that, you're going to make this thing look dipolar because the field of any source at a large enough distance turns into the field of a dipole. So if you do that, this is a synthetic source here on the left. You can see the map in the middle. It looks pretty dipolar. However, because this is a synthetic source, I can also compute the exact field at that second height. And if you take the difference between those two maps, you get what is on the left in B. And you see that there's an error associated with the process of upward continuing a map, even in the absence of noise. And why is that? Because upward continuation, although it's numerically stable, it's only exact if you know the data all over an infinite plane. And because we are mapping this, even though it looks like it's zero at the edges, it's not really zero at the edges. And what we derived were the equations to compute this error. And essentially, this error is related to everything that is outside of the mapping area that you didn't measure. And it concentrates around the edges of your map. So what I'm showing here is the calculation of the error, expected error, On the left is the true error, and here's the difference of the errors. So to show that the error predominantly comes from the fact that you have a restricted mapping area. In this case, because there's so much space around the actual source, you're able to upward continue this and still have a fairly low error. But if you were like in more realistic situations, that error would be much bigger. And then if you try to do a dipole inversion of this, you're going to start to get significant errors in your moment estimation. Roger and I and other people from his group, we worked on a paper. People working with the QDM are probably familiar with that, where we analyzed this trade-off of how much can you upward continue and still get reasonable accuracy in your estimates. Okay, so having understood that it's not going to bias a lot in terms of how complex of a source we can invert. Let's go back to this idea of this linear operator relating magnetization to magnetic field. And now the idea is, can we perform mathematical operations on the data, on the field that you measure, that translate into other mathematical operations on the magnetization? And this is one of the methods that we worked on for estimating net moments of complex sources. And the idea is that you're going to compute moments of the magnetic field. And I know this sounds confusing because we're talking about net moments and I'm talking about moments of the field, but this is a mathematical term. Whenever you integrate a function against one of its independent variables, you're computing in mathematics what is called a moment. So if we do these operations, notice that there's no inversion involved here explicitly. All you're doing is performing operations on the field, and that is hopefully going to help you estimate the net moment. For this technique to work better, you actually have to take data on multiple areas, because then you're going to get different equations and you can combine them to improve convergence and to also being sensitive, for instance, to a constant uncertainty. All this magnetic microscopy data, they have an arbitrary constant added to that because you don't have absolute magnetometers. So you can have a small constant added to your map, and you don't want that to spoil your estimates. I know this is ugly, but let's just see. These are the three integrals. Mathematicians, for some reason, they don't like to call things X, Y, and Z because they live in higher dimensional spaces and they run out of letters. So they call things by indexes, like 1, 2, and 3. So B3 is BZ, okay? X1 is X, X2 is Y, X3 is Z. So essentially what we're doing there are integrals of BZ against X, against Y, and against a constant. And what you see is that these integrals give you the moment, which are the things within brackets, components of the moment, plus higher order terms that depend on inverse powers of your mapping area. So as you enlarge your mapping area, these estimates are going to become more and more just dominated by the net moment. Of course, you need to use very large areas for that thing to attain an asymptotic regime. And what we do is that we then, because we have the theoretical equations for that, you can do fits and use the data that you have to constrain the behavior, how these things are converging, how those integrals are converging, and then you can estimate using smaller areas. A fairly powerful extension of this idea, but very complicated, is another thing that we develop. I'm not going to talk in details about this. For those who are interested, this is the paper where we discussed this, the Bowden extremal problem. And the idea is that instead of using just simple polynomials to compute those integrals, you're going to find functions phi that you can integrate against your B, and that is going to give you estimates of the moment. And the power of this thing is that now you can assess the moment of a region within your sample, not necessarily your whole sample. But then what I would say worked best is the method that we have been developing for, I don't know, 5 years or so, which is using multiple expansions based on spherical harmonics. The idea, the motivation for this was like, okay, we have a dipole. What if we add a quadrupole? What if we increase the complexity of our source model? Can we model more complicated sources? This is just for people familiar with the IGRF model. This is just the regular spherical harmonic expansion. Why are we choosing spherical harmonics if the geometry is not spherical? Because it's spherical. Spherical harmonics expansion have a very interesting advantage, is that all of the net moment is concentrated in the first 3 terms, which is the dipole terms. So all you care is to estimate the first 3 terms of the multiple expansion. Ugly equations, but just like the dipole, notice that now the constants are in white. You have constants that are multiplied by functions. And so this is, as long as those functions are defined, this is a linear problem. But again, where do we put the origin of the multiple expansion? And this is essentially unconstrained, because by definition, you can put the origin of the multiple expansion anywhere. And as long as we have an infinite expansion, you're going to get a multiple expansion that exactly represents your data. So we cannot work with infinite expansion, so we're going to truncate that expansion. And when you truncate the expansion, it makes a big difference where you place the origin, because you're going to converge or not converge depending on where you are. So again, we solve an optimization problem to find the origin location. And for each guess of where the origin is, you solve a linearly square problems to determine all of the coefficients of your multiple expansion. Okay, so enough of equations. How do multiples like on the plane? That's how they look like. So if you take those, the dipole terms, the quadrupole terms, octupole, and so on, here's what they look like. And you can start to notice something that is very interesting and why this problem is complicated. Look at these 3 first quadrupole terms and how similar they look to dipole terms. Now look at the octupole terms and look how similar they look to these terms. And the problem is that on a spherical setting, spherical harmonics are an orthogonal basis. When you are on the plane, that's no longer true. So essentially you have like 2 vectors that are getting closer and closer to each other. And now to be able to separate those things is going to be a little tricky. This is the 64 pole. If you want to look, it's beautiful patterns. I want to make a t-shirt with this, but so let's get down to real applications of this. So here I'm showing how this works when you have a lot of noise. This is a synthetic source. Why do we do synthetic sources? Because with synthetic sources, you know exactly what solution you should get. So that allows you to compute the error in your estimation, right? And once you understand how your technique works and where it doesn't work, then you can move on to applying to other things. By the way, the whole multiple thing is a paper that is going to appear soon on G Cubed. So all the details of this, you'll be able to read it, grab a big cup of coffee because it's a big paper. So what we can see here, the blue curve is when you have no noise. So when you have no noise, the higher you go on the degree of your, here's my cursor. The higher you go on the degree, the better you estimate your moment, right? So these black lines are 10%, 5%, and 2% error for your reference. So you can go to like, you can keep going, 0.1, 0.01. As soon as you put noise, because you will see that this becomes sensitive to noise, because now noise is going to start impacting your net moment estimation. You're going to decrease up to a point, and then the estimation error is going to go back up. But even with this horrible one-to-one noise, signal to noise ratio, without any added regularization, you can get below 10% there. And here's showing just that the residuals keep decaying as expected, right? Spherical harmonics are gonna, in multiple experiments, are gonna model whatever you put there. A point of interest is to notice, see if my cursor reappears here. You see that you're starting to get voids in your residual maps. That means that you have so many degrees of freedom that now you're modeling the noise. And that's one of the reasons why your net moment estimates get messed up. If you introduce regularization, you can bring that noise down. Just for the people that know, this is SVD truncation, what we do here. We throw away some singular vectors and singular values, and by doing that, you decrease the sensitivity to noise. And you can bring errors that were originally, because I think it's for the 3-to-1 signal to noise ratio, that were originally around 5%, you can bring them down to below 2%, maybe to 1.5%. Okay, so let's get to the fun part. We wanted to solve the speedotem problems, right? So let's apply that to speedotems. This is a Portuguese speedotem, and the Eric Font, the collaborator, collected and analyzed on the 2G. In the middle here are the samples that the part that he used for the 2G, and we got slices. And part of the problem with the slices is that they are not, of course, from the center, because the center was used for the 2G. So you can see that the layers have some curvature there. Okay. So we cut this into small pieces, and these are the magnetic microscopy maps of the NRM of those pieces. These are the Zydeville diagrams. And for people that are going to say, oh, they're noisy. Yes, they're noisy because you don't have enough magnetic minerals there. Most of the noise comes from the sample itself. It's not the noise of the inversion. It's not noise on the magnetometer. And that's the other beauty of magnetic microscopy. When you apply an AF, you see these things bouncing around. You can see on your map. You can see that you're changing. So those are two pieces, the other two pieces. And here's the comparison. So the Blackstar is what was measured with the superconducting rock magnetometer, the 2G. And the other four measurements, or the four directions you see there, the components that we computed from those Zydevilles. And you can see that there's a little bit of difference in inclination, which is expected because, as I said, we are dealing with the part of the speedotem that is already curved. But you can also see that instead of one data point, we can actually get four, and I would argue five, because just the thickness of what you're measuring is 5 times smaller than the thickness of the original 2G slabs, which means an improvement in the temporal resolution of your record by a factor of 5. To test how stable these pieces can acquire, they can acquire stable magnetization, we use ARM. And here you see that they are reasonably okay in terms of acquiring ARMs. For those that were on the Magic workshop, Kawe Borlina showed more of this and how we are using repeat applications of ARM to try to quantify just the uncertainty in the sample itself acquiring a magnetization. So what are the next steps? I met Roger on the plane, and we were already like, okay, time to get this to the QDM. Because part of the problem is that when you get the data that the QDM measures, which is along a crystallographic direction, and you convert that to BZ, there's an error, much like the upward continuation that I was showing. There's an error associated with the process. And if you try to do these inversions with that error included, you're going to be compromising your accuracy. So we need to adapt this to work directly on, let's say, raw QDM data. the asymptotic method worked okay, but when we started putting squid microscopy noise, we started getting very large variations in our estimates. So we want to, this is weird. Okay. So we want to make sure that we continue to improve that. I have hopes that this is going to behave better for the QDM. And then also keep improving and devising new regularization methods so we can keep getting better and better estimates. And then this is also something that we are working on actively now, is to look for other basis functions that are not spherical harmonics that may have some interesting properties in terms of the convergence of the net moment. That was all. Thank you.
Okay, so we only have time for maybe a couple questions, but just like in morning, this time after. Really?
Okay, nice one. I have one question. What about if, you showed that multiples produce a bunch of anomalies? Yeah. What about if the same bunch of anomalies is produced by a group of sources that are close to each other, but they are not one spot? If you apply spherical harmonic methods, how good will be your estimate of the total moment? Is the total moment comparable with the sum of individual moments of your sources?
So the multiple expansion and the spherical harmonic expansion in particular, it's, first of all, it's translation invariant for the first term. So for electrostatics, you have the monopole term. So the monopole term is translation invariant. So no matter where you put your origin, you get the same charge, right? Because that is associated with the physical quantity. The same thing here. The fact that you're playing with the non-uniqueness of magnetic fields, right? Multiples can be seen as a concentration of dipoles around the origin, separated by an infinitesimally small distance. Those are not your real sources. You don't care. What you care is that the dipole moment is the net moment. And that is a subtle step. There's a very important step that sometimes people don't appreciate, is that it's tied to a physical quantity. So even though the magnetization itself may have nothing to do with quadruples or octupoles or anything like that, the fact that the dipole moment is the net moment, that is what ensures that even though that the expansion doesn't represent your physical magnetization, your dipole moment represents your net moment. Does that make sense?
Yes, thanks.
Okay.
And my second question is, you're saying that you're exploring other functions to use to the problem. So are you thinking about a set of functions that are orthogonal on the plane?
Yeah, so actually the SVD gives you that, right? SVD is a numerical version of the single value expansion, like if you look into functional analysis and function spaces. So that is going to give you automatically an orthonormal basis on the planar setting. And I didn't show this here because I didn't want to talk too much into the details, but it's very interesting to look at the left singular vectors and see how they compare to your multiples. But still, they have some undesirable properties that like higher order terms carry that moment. And that's the problem. Like if you go to the higher order terms, you're susceptible to noise, and that's why your estimates are being affected by noise. So we're looking at different possibilities. One of them is Kelvin transforms, which are transforms that are used in potential field theory, for instance, to transform the inside of a sphere to the outside of a sphere. So we play with that from transforming a sphere onto a plane. And that can potentially give you a good set of basis functions.
Thanks.
Okay.
Thanks. So my question is perhaps the same as Ramon's. I'm not really sure, but since you are working on a flat Earth, why are you not using a 2D Fourier transform, which naturally separates things according to wavelength in the same way as people would do if they were looking at anomalies on the seafloor, and you could then calculate the presence of the equivalent dipoles that are producing your signals? Is there a reason for that?
Yes, so the reason is, again, that was my first question. I kept pestering the mathematicians. I said, can't we just transform whatever we have from spherical harmonics onto the plane, right? And when you transform that, you see that there's all these mixing happening. So the moment information is no longer concentrated on just 3 coefficients. And so if you use, again, we're trying to avoid solving an inversion for the sources, right?
But isn't that what you would want to do?
Yes, yes. But there are the questions of how well can you estimate? I understand your point. Like, why not use functions that are defined on the plane that are orthogonal or something like that? When we tried to do that, it was numerically, it wasn't like the obvious choices weren't that great.
Well, sorry to go on about this, but of course it's unstable because it's an problem.
Yeah.
But there's also a fair amount of evidence from looking at seamount data that if you just do something like analogous to the least square snip to the directions in there, then you end up with a result that's quite biased. And you're telling me that you're not susceptible to it.
No, I'm telling you that we're very, look, I'm convinced that this net moment problem is the wall. We tried to come at from many different ways, and we hit the same wall no matter where we come from. We tried Fourier techniques on the plane. You can show that around the origin, because the Fourier at frequency 0 is your net moment. So if you try to estimate Fourier around the origin, you have lots of issues with that. You can estimate 2 of the components well, but not the third one, not the ratio between the components. So there's some intrinsic opposedness to this that I think no matter which direction you approach, you're going to hit the wall. The question is, which ones are less susceptible to noise and things like that? And I think that would make a difference. Like we are keep trying other possibilities and see which one is going to give us numerically more stable solutions and faster convergence.
Maybe 1 or 2 questions? Anybody? Okay. Same for
Yeah.
Okay. Okay.